Ladies and gentlemen, welcome to Engineering Dynamics. In this video, we will be talking about velocities in moving and stationary, also called inertial, coordinate systems. Let's jump right in. We are given this example. We have a pendulum with two bodies. We have body 1 right here and body 2 right there, and they are, of course, connected. And our goal is, first of all, to find out how many degrees of freedom this body has. We're talking about a body and not just a point mass. A point mass has just 3 translations, that's x, y, and z, and no rotations because a point is a point and not a physical object that you can turn. So for a point, we have only 3 degrees of freedom, but for a body, like in this case, we have x, y, and z, so the translations in 3D space, and then we have the rotations, so rotation around x, y, and z. So for one body, we have 6 degrees of freedom. But of course, we also have the constraints. So that's our r's. So we have 6 times n. So the number of bodies that we have is n. 6 is our possible degrees of freedom. And then we have to subtract our constraints. One constraint is, for example, like here, the connection. So that the two bodies are not just independently in space, but we have a connection here and of course a connection there. So the next thing is we just write everything out as if we had no constraints. So body 1 has x, y, and z, and the rotation alpha, beta, and gamma. Then of course the second body has also x, y, and z, and the rotations alpha, beta, and gamma, but in this case for the second body. And together we have 12 degrees of freedom. But now that we're only talking in a 2D case, we don't have a z direction to go through, and we don't have the rotations around y and the rotations around z. So we eliminate the z translation, and we eliminate beta gamma of the first body and beta gamma of the second body, because they are 0, because we are in 2D. So we eliminated 6 degrees of freedom. And from that, we now look at the constraints. Can we formulate the positions of our body in such a way where they are only dependent on one, like, general coordinate? In this case, we choose alpha and beta. So we can say that x is always, x1 is cosine alpha times L, and I'm sorry, that's the wrong one. x1, and that's supposed to be a 1. So x1 is cosine alpha times L, and y1 is sine alpha. So we're talking about this point right there. And then we have the center of gravity of our second body. So we have x2 is cosine alpha 2L, because we have to go all the way, and cosine beta L right here. And for y2, we have sine alpha 2L times plus sine beta times L. So we have 4 equations, and we again eliminated 2 degrees of freedom. So we go from 12 minus 6 minus 4, and we are left with 2 degrees of freedom. We, for example, could choose alpha and beta or alpha and gamma. So let's have a look. We have alpha, and now we can choose if we want to go by beta or by gamma. And we go with the first option. So we choose as our generalized coordinates, we choose alpha and beta. And now we want to find the absolute velocity of point B, that's that one, in coordinate frame I. We have coordinate frame I right here. So the absolute velocity of point B in I is just the time derivative of our position, that's r, of our point B in I. So we have to first find the position of our point B, again, this one, in coordinate frame I. And we know that to go from the origin right here into direction x, we have to first go the cosine. That's this one. Cosine 2L alpha plus the cosine of this one. So cosine beta plus times L. So we are here. And we do the same thing for y. We have sine 2L, that's right there, and then plus sine beta L. So right there. And we get our position. Now we just have to derive it once in time. So we derive by alpha and of course by beta, and we are left with our velocity that we're actually looking for. And now we can compare this velocity to the velocity of point B in coordinate frame K. So that's what we now want to find out. We want to find out B in coordinate frame K. The first thing we have to do, of course, is get a time derivative of B and K, but then we have to also consider the rotation of the coordinate frame K itself, because as the coordinate frame is turning, so has to the point. The point has to be turning as well. So this is our angular velocity and our position. In coordinate frame K, we have, let's remove everything right here. Let's make it bigger. Here we go. So in coordinate frame K, right there, we have to go 2L in direction X, that's right there. And then we have to go gamma. But we didn't choose gamma, we chose alpha and beta. And we know that gamma is just beta minus alpha. So that's what we do. We go 2L into the X direction, and then we have to go cosine beta minus alpha times L. For the sine, for the Y direction, we just have to go the sine of beta minus alpha times L. So maybe we have the sine and it is right there. That's the sine. Now we have to do the cross product of the angular velocity and the position vector in our coordinate frame B. Our angular velocity is alpha dot, because this is our alpha at the moment, but alpha is changing. That's why our velocity is alpha dot. So we have alpha dot cross our position, and we go this one plus this one minus this one plus that one. So we're left with alpha minus this one. The second term is this one times this one minus 0, 0. So we are left with 2L cosine alpha minus beta times L. And in the third direction, nothing is happening because we have, oh, sorry for that. We have 0 times something and 0 times something. So we're left with 0. And now we have just to add this one and the time derivative from that with this one. So when we combine those two, we have the velocity of point B in coordinate frame K. And if we now want, of course, to find, if we just did the first operation, so let's say this one, we can find the velocity of point K, of point B in coordinate frame K by transforming the velocity of point B in I from I with the transformation matrix in K. I have some videos about the transformation matrices, so you can just check them out. And this video is just an introduction on how to transform, on how to get the absolute velocity in a stationary coordinate system. So you just get the vector to that point where you want to find the velocity, and you derive it once with time. But this is only possible in the inertial coordinate system. If you have a moving coordinate system, you have to first, like I said, find the vector, or basically the position of the point where you want to get the velocity from, derive it once with time, but also consider the velocity, or basically the rotation of that coordinate system. So that's why you have this additional term in the velocity when you are not in a inertial coordinate system, but this time in a moving coordinate system. I hope this video gave you a small introduction to degrees of freedom and constraints. If you have any questions, you can put them in the comments down below and I will do my best to answer your question. Thank you very much for your attention and see you next time.